Hello, Assalamualaikum. My name is Muhammad Ihsan. I want to explain 4.1 completing the DFT. First of all, the coding is generated using the function x equal DFT equation x to implement the DFT of the equations. First, define n equal to 10 for point vector. Second, define n equals 0 and minus 1 for loops. Continue with xn, same like following cases in procedure like this. So we discard one by one. So x1, x2, x3 and x4. This time call the function to compute the DFT of the signal x1, x2, x3 and x4 like this. Now it's time to produce the graph to see how the output. First, for x1, x2, x3 and x4. For the inverse cases, we define same like above, x1 underscore r1, r2, r3 and r4. For the inverse DFT, using subplot and solver, we have 4 signals to produce. First, second, third and fourth. For the xk, like this one, we define n equal 0 and minus 1 for k equal 1 and used for loop compute the DFT of the signals. This is equation xk equal like this, and then the functions of xn like this. So we end. So now we go one by one. First, figure 1 is for x1, x2 for figure 2, x3 for figure 3 and x4 for figure 4. So the graph of xn combining with xk. So we can get like this for the inverse and xn, figure 6, figure 7 and figure 8. So that's all from me. Thank you.
I'm Farzana Fasihah. So now I would like to continue the presentation for part 4.2, that is matrix representation of the DFT. So in this part, we have 4 procedures to complete. For the first one is we need to write the MATLAB coding. Okay, MATLAB coding for function A equals to DFT matrix N. So in this part, we just write the coding, no need to simulate. So first we declare the function A equals to what? Okay, function A equals to the DFT matrix N. And then for A, since A equals to N times N matrix, so we just declare here what is the value of matrix. And then by referring the expression here, the equation here, okay, we declare for K from 1 to N and also same to N from 1 to N. And then we end here for the MATLAB coding number 1, and we proceed to number 2. Number 2, we need to compute the DFT according to these 3 signals, okay, given in the lab sheet. So for the first one, we need to declare first the character that we will use, such as n is how much samples that we want to run. Okay, so let's say here it gives n equals to 10, so we just declare n equals to 10. W is the expression that we will use to calculate, okay, and A is the zeros n until n. Okay, so for the first signal, okay, for the first signal is x equals to 1 zeros, 1 from 1 to 9, and then after we define the value for xn, we need to compute the DFT of xn here. Okay, to compute it, we need to declare capital X equals to small x times by A. Okay, and then after we declare the function here, the expression here, okay, we need to add up some function, okay, to produce or to obtain the result. Okay, So this is the figure command to produce the figure of the simulation. The stem function here is used to give label for the x-axis and y-axis, and the title is just to put the title in the figure that we will obtain. Okay, so proceed for the part B. Same goes to part A already. Just we need to declare based on what the question given here. Okay, so for the x2, we start from 1 until 10, and then same goes to here. We compute the DFT by multiplying x2 times A, and then same, we put the figure command, we put the stem, okay, x label as k, y label as stem height, and the title is DFT unity. And then grid on. Grid on is the last command for producing the graph. Okay, and the last one is for the question C. Okay, after we define the xn, that is from 0 until 9. Okay, from 0 until 9. Why? Because we need to have 10 samples. So from 0 until 9, we have 10 samples. And then this is the expression here for the calculation. And then these 4 commands for producing the graph after we simulate. Okay, so for the output of the FT signal, here we will get after the simulation. Okay, and okay, this is where we separate the coding for the each part. Okay, so this is for the part A for n equals to 10. Okay, after we run the simulation, okay, we got the graph here. Okay, SK is the x-axis, stem height for the y-axis, and all the graph is in same line, same height with the from 10 until 9. So here we have 10 samples from 0 until 9. This is for the part B. Same coding we use. Okay, and for the result here, we also have 10 samples from 0 until 9 with the same stem height. It is at 0. And the last one is for the part C. Okay, this is the question for part C. Okay, same, we have 10 samples. 10 samples from 0 until 9. Okay, just for this at value 1 only, it has the value of 10 for the stem height, and for the rest is all of them is at the 0 axis. Okay, so I think that's all from me. I will pass to ZAFIRA.
From the previous result with the DFT, the inverse DFT may also be represented as a metric vector product, which is from question 3a. We can see that since the x equal to bx and DFT of xk is xn equal to sum of n and k equal to 1 of bnk times xk, so that the analytic expressions for the inverse DFT of matrix B will be as these equations. For the question 3b, we need to write a MATLAB functions of B equal to IDFT matrix N that returns the nxn's inverse of DFT matrix. As we can see, we have to derive the functions of B equations to IDFT matrix N, and then derive the value of N, which is equal to 5. Next, we write the code to make the IDFT matrix. We'll calculate the n by n's IDFT matrix as this. And then we enter the equations of the analytic expressions on the MATLAB so that we can get the answer result as this from the command window here. Next, for the question 3c, we need to write a code for compute the matrix A and B for n equal to 5. Then we need to compute the matrix product of C, which is equal to B times A as shown here. And then for the result, we can get the DFT matrix of A for n equal to 5 we'll get as this, and the IDFT matrix for n equal to 5 we'll get as this, and lastly we can get the product of C equal to BA as this. From this part, the DFT also can be implemented as a metric vector product, and to see this we will consider to the equations of x equal to AX. Then we will enter into the MATLAB code to get the 5 points DFT and IDFT of 1, 2, 3, 4 and 5 as x equals to this. So we can get the result at the command window here. Furthermore, for question 4, we need to compare our answer of DFT equations x from part 4.1 and DFT matrix n from part 4.2 with the built-in MATLAB functions of FFTX. Then we just replace the functions of DFT equation s and DFT matrix n as FFTX at the MATLAB coding here, which is to compute the DFT of the signal of x1n, x2n, x3n, and x4n, which is for both parts as shown in the command window here. So that this is the result that we get from the command window for part 2 in questions 4, so that we can get the result here. And that's all for questions 4, and that's all from us. Thank you.